The length of 1 degree of the Earth's meridian gradually increases towards the poles. This scientifically proves that our planet has the characteristic oblate shape of an ellipsoid of revolution. The complex equipotential surface of the planet, fully coinciding with the mean ocean level, is called the geoid. Studying the exact shape of this surface allows scientists to effectively investigate the internal structure of the core.
You know, we all grow up with this idea that the Earth is a perfect sphere, right? That beautiful blue marble floating in space. But what if I told you that familiar image, while it's definitely beautiful, is fundamentally wrong? In this explainer, we're going to dig way past that simple idea. We're going to use the principles of geodesy to uncover the true and honestly the surprisingly complex shape of our planet.
So let's just start with that big, basic question. Is the Earth a perfect sphere? For centuries, that's been our default model. It's our geometric shorthand for the world. But is it scientifically accurate? Well, the answer isn't just a simple no. It's a no that actually kicks off a much more fascinating and dynamic story about our planet.
So here's how we're going to break this all down. First, we're going to dismantle that myth of the perfect sphere. Then, we'll start building up a more accurate model, starting with a good first approximation called the ellipsoid. From there, we'll move on to the Earth's true physical shape, which is the geoid. And finally, we'll get into why this level of precision is so incredibly critical to our modern world.
All right, let's dive right into the evidence. You see, the first clues that the Earth wasn't a perfect sphere didn't come from some abstract theory. No, they came from scientists actually going out and performing these incredibly painstaking measurements of the planet itself. Okay, so starting way back in the 17th century, geodesists began this really ambitious project to measure the exact length of a 1-degree arc of latitude at different spots on the globe. Now think of it like this. You're measuring one slice of a 360-degree pizza that is the planet. And what they found presented a real puzzle. Down near the equator, that 1-degree slice measured about 110.6 kilometers. But here's where it got really interesting. When they did the exact same measurement, but this time closer to the poles, they got a longer distance, 111.7 kilometers. So what does that mean? Well, to cover that same 1-degree angle, you had to travel a greater distance along the surface. And that can only mean one thing. The surface at the poles is actually flatter. It's less curved than it is at the equator.
And this chart just lays it out side by side. You can see the difference plainly. This was not some measurement error. This was hard empirical proof. The Earth is not a perfect sphere. It's actually slightly squashed, a shape we call an oblate sphere, a little flatter at the poles and bulging out at the equator.
Okay, so if it's not a sphere, what's a better model? This brings us to our first major upgrade in understanding the Earth's shape, the ellipsoid of revolution.
So what is an ellipsoid of revolution? Well, it's the 3D shape you get when you take an ellipse, basically a stretched out circle, and you spin it. For Earth, this shape is a direct consequence of its rotation. I mean, the immense centrifugal force from the planet's daily spin causes it to bulge outwards along the equator and get compressed along the polar axis. And the result is this very specific shape, the oblate spheroid.
This diagram really illustrates the geometry perfectly. That dashed line, that's our old friend, the idealized sphere. But the solid line, that's the more accurate ellipsoid. And you can clearly see that the distance from the center out to the equator, that's the semi-major axis, labeled A, is longer than the distance from the center to the pole, the semi-minor axis, B. And that difference is what defines the Earth's flattening.
You know, what's truly amazing is how our measurement of this ellipsoid has been refined over the years. This table compares calculations from 1940 with more modern ones from 1979. And if you look closely at the numbers, we're talking about refining the radius of the entire planet down to a matter of meters. It's incredible. As our tech got better, from ground surveys to the first satellites, our model of the Earth just got more and more precise. And for modern science, trust me, every single one of those meters counts.
But here's the really crucial point. Even this highly precise ellipsoid is still, well, too perfect. It's a smooth, clean mathematical shape. The Earth's actual surface is far more complex, far more irregular. And to understand that, we need to introduce our final and most accurate concept, the geoid.
Now, to really get what the geoid is, we first have to understand something called a level surface, or more technically, an equipotential surface. Just imagine the entire Earth was covered in a perfectly still global ocean, with no tides, no currents, nothing. The shape that ocean's surface would take, molded purely by gravity, that is a level surface. At every single point, the force of gravity is pulling straight down, totally perpendicular to the surface.
So the geoid is simply one specific, level surface Out of an infinite number of them, it's the one we've chosen because it best matches the average sea level across the whole globe, and we just imagine it extending invisibly underneath the continents. But here's why it isn't smooth like the ellipsoid. The mass inside the Earth isn't distributed evenly. You've got super dense mountain ranges, less dense ocean crust, variations deep in the mantle, and more mass means a slightly stronger gravitational pull. So this ocean surface has hills and valleys, all created by the uneven gravity of the planet beneath it.
Let's put them side by side. The ellipsoid is our clean mathematical model. It's a perfect, simple reference frame that's absolutely essential for making maps and doing calculations. The geoid, on the other hand, is the physical reality. It's the complex, irregular surface that the Earth's gravity actually creates. You could say one is a necessary ideal and the other is the real world.
So just how irregular are we talking about? Well, these gravitational bumps and dips, they're called geoid undulations, can vary from that smooth ellipsoid by up to 100 meters in either direction. And remember, these aren't physical mountains you could see. They're invisible hills of slightly stronger gravity and valleys of slightly weaker gravity.
Okay, so we've got a smooth mathematical ellipsoid and this lumpy physical geoid. Why does any of this deep scientific detail actually matter in the real world? Let's put it all together.
This diagram here just brings all three concepts together beautifully. So at the bottom, we see that smooth, dashed line of our reference ellipsoid. Then you see the wavy, irregular line moving above and below it. That's the geoid, the true gravity surface. And sitting on top of that is the physical topography we all know and love, the actual mountains, plains, and ocean trenches. You really need all three of these layers for a complete scientific picture of the Earth.
So why do we obsess over these details? It's actually pretty simple. The GPS in your car or on your phone, it relies on an incredibly precise model of the geoid to calculate your position. Oceanographers who are tracking sea level rise down to the millimeter, they depend on it. And what's really profound, by studying the subtle hills and valleys of the geoid, geophysicists can actually map out density variations deep inside the Earth. It gives us a window into the dynamic processes happening in our planet's interior.
So let's just end with this thought. The shape of our world isn't some static geometric form. It is a dynamic fingerprint of the forces that are churning deep inside of it. Every little bump and dip in its gravitational field is a clue about the colossal hidden motions of rock and metal down in the mantle and the core. The seemingly simple question, what is the shape of the Earth, is still leading us to brand new discoveries about the secret inner life of our planet.
Thank you, friends. Strive for understanding and become wiser. See you soon.